All right, welcome. Hope you're enjoying the snow day. We are going to be talking about reduction of order today. So in section 4.1, we started off with our journey of trying to figure out how to solve like second and third order like linear differential equations. So here we have a second order ODE. And the idea for today is a little bit weird. The idea is that like let's assume that we already have one solution and say if we do already have that one solution, how are we going to use that solution, or how can we use that solution to find a second solution that is linearly independent from that first one. And the way that we're going to be doing that is called reduction of order. So the idea of how reduction of order works is basically it takes this second order differential equation and we're going to basically reduce it down to a first order differential equation, which we already know how to solve using the integrating factor method, right? We find our mu of x is equal to e to the integral of like the p of x, blah, 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 that whole thing. That's the integrating factor method. Reduction of order is basically just we're going to take this sort of thing and just knock it down to a first order thing, assuming that we already have one solution. So this is very contingent on already having a solution. So if you don't already have a solution, you have to find that solution somehow else. But this formula is probably more useful than you expect it to be the first time that you see it. But anyway, let's get into it. The first thing that we're going to do is we're going to start with assuming that y2 of x is equal to, let's say, u of x times y1 of x, where u of x is some non-constant function. Why is it non-constant? Well, we need y2 and y1 to be linearly independent. And if this was constant, if you had like y2 is equal to like a constant multiple of y1, then they would not be linearly independent. They'd be constant multiples of each other. So we're like this is like an assumption that we're kind of placing on here, that and this assumption just kind of works out just fine. All right, so if we assume this, what can we say? Well, then we can compute the derivative y2 prime and then y2 double prime, and then we can plug all of that information into this differential equation up here. We'll probably want to normalize it, so let's go ahead and normalize right away. So let's normalize this by dividing by that that a2 of x, and we basically get y double prime plus p of x times y prime plus q of x equals 0. And that's what we get after normalizing. Now we're going to plug y2, which is this, into this, and then see what we get. So let's compute y1 prime and y2 double prime. Y2 prime, y2 is equal to u times y1. I'm going to stop writing the of x's all the time. Just going to get a little tedious and messy if we don't stop. So product rule, I get derivative of u times y1 is u prime times y1 plus u times y1 prime. And then the second derivative, I'll do the derivative of this thing first using a product rule, and then the derivative of uy1 prime using a product rule. So I'm going to have like 2 terms from each of them, so 4 total before we simplify. We want derivative of u prime first. Derivative of u prime is u double prime. Keep y1 the same. Then we'll keep u prime the same, and then take the derivative of y1 prime. Now we'll take the derivative of u y1 prime. The derivative of u is just going to be u prime. The derivative of and then y1 prime we leave alone. Now we'll leave u alone, and then take the derivative of y1 prime, so y1 double prime. We should notice that these two terms here are the same, so we can just combine them into 2 times u prime y1 prime. So this is equal to u double prime y1 plus 2 u prime y1 prime plus u y1 double prime. So now we have our y2 prime, and our y2 double prime. And we can plug all this stuff into our normalized differential equation up here. Maybe let's copy paste that. Copy paste. And then put some 2's in here because we're going to plug y2. Oh, I messed up. There's supposed to be a y over here. This should be times y. Forgot about that y right there. Let's put the y. Y2. Make it black. Why not? Okay. So we're plugging y2 double prime, y2 prime, and then y2 all in there. Y2 double prime is this whole business. That's y2 double prime. P of x, I'm just going to write as p, times y2 prime. Y2 prime is u prime y1 plus u y1 prime. And then q times y2. Y2 is just u times y1. And this is equal to 0. So this is super messy, but we're going to be able to simplify this down to something a lot nicer, and this is how we're going to do it. It's basically going to utilize the fact that if I were to plug, let's make this blank again. If I were to plug y1 into this differential equation, this normalized differential equation, y1 double prime plus y1 prime plus q times y1, that should, if I plug y1 into that differential equation, that'll give me 0. So if I'm able to find this showing up in my differential equation down here, then I should just be able to replace that with 0. And that's going to be the idea of what we're going to do. Let me get rid of those just for sake of keeping clean notes. All right. So let's distribute everything first. So I'm distributing p times u prime y1 plus p times u times y1 prime plus q u y1. So if I can find this showing up with like y1s in places, or maybe a constant multiple of that, then we should be good. So we have like u times qy1 showing up here. So like pretty much everything here is like multiplied by a u somewhere. So let's highlight some stuff. So this shows up there. So again, we're looking for y1 double prime plus p y1 prime plus q y1. So we have that. That's basically this term times u. And then we have, do we have a u times y1 double prime? Yeah, we do right here. So these three things are basically just u times this whole thing, which is going to be equal to 0. So let's copy all the stuff on here. So this plus all that highlighted stuff, we can factor out a u from it, be left with y1 double prime plus p times y1 prime plus q times y1. And that is all going to equal 0 because y1 is a solution to the differential equation. And so we get u double prime y1 plus 2 u1 prime y1 prime. Sorry, that should not be u1 prime, that should just be u prime. Kept doing that up there as well, so there's too much notation going on here. Plus p u prime y, and that y should be a y1. And that equals 0. Okay, so yeah, all right, good. So, all right, next thing we're gonna do is we're gonna do like a substitution. So we're gonna replace u prime with just w. So we're gonna call w equal to u prime, and so w prime is equal to u double prime. So anytime that I see a u double prime, I'm going to replace it with w prime. Every time I see a u prime, I'm going to replace that with a w. And we get w prime y1 plus 2 w y1 prime plus p w y1 equals 0. I could rewrite this slightly as y1 times w prime plus, and then from these two terms here, I can factor out a w and be left with 2 y1 prime plus p y1 times w equals 0, which is a first order linear differential equation. So what I said before about how we're going to take this second order differential equation and this y1, which is something that we already know to be a solution, and reduce it down to something that we know how to solve, a first order differential equation we know how to solve. We know how to solve linear first order differential equations. So this thing right here is just literally something linear. And so we can just do the integrating factor method on it. So, so what's the integrating factor method tell us to do? Well, first thing that we have to do is normalize. So here we're treating w as like the function that we are trying to find. So we'll normalize by dividing by y1. So we'll normalize first. And we get w prime plus 2 2 y1 prime over y1 plus, here we'll get like p y1 over y1, but the y1s will just cancel and we'll just be left with p. This is all times w and is equal to 0. What is our integrating factor? Our integrating factor is mu of x, which is equal to e to the integral of whatever our thing that's being multiplied by w is. So a little messy, but it's equal to 2 times y1 prime over y1 plus p dx. All right, so this we can simplify this a little bit. There's a tricky little integral thing that we can do here. So I can pull out a 2 from that first thing. This is like y1 prime over y1 dx, and then plus the integral of just p of x dx, which I could rewrite as e to the 2 integral y1 prime over y1 dx times e to the integral of p of x dx. Did I need to do that? I don't know if I needed to do that. Can't remember if I needed to do that or not, so I'll maybe save that for later. Let's worry about this integral right here for now, actually. Okay, so this integral right here, we can do a like a substitution. We're kind of running out of variables, so if you want to think of it in terms of variables, just call v equal to y1, and then dv will be equal to y1. So like the y1 is like really y1 of x, right? So dv would be y1 prime of x times dx. I put the of x there just to sort of remind you that this should be like times dx. And so if you do that, this would be equal to e to the 2 1 over v dv. And so this is going to give us ln of v, or ln of y1. So we get e to the 2 ln of absolute value of v, which is just y1, plus the integral of p of x dx. Okay, yeah, I did want to do that thing with the e's. This is like times e to that integral. Okay, cool. Cool. All right, so then this boy right here, e to the 2 ln of y1, is really just e to the y1, e to the ln of y1 squared. I can drop the absolute values because y1 squared is always positive. So this is y1 squared times e to the integral of p of x dx. All right, so that is our integrating factor. So then we would multiply both sides of that starred equation up there by our y1 squared times e to the, well, maybe I'll just say times mu of x. And I'll skip a couple of steps right here just for sake of time, and because I already worked this out and I know that it works just fine. But normally I would recommend writing out all your steps and checking everything, just make sure you don't have any errors. But you should end up getting on the left side the derivative of your mu of x times w, and the right side you just get 0 because 0 times mu, blah, blah, blah. And I'm running out of space. Let's make a little bit more space. So you get mu of x, which is really y1 squared, times e to the integral of p of x dx, times w, and remember what w was? W was equal to u prime. And that is equal to the integral of 0 dx, which is just a constant. And we're just looking for a single solution. So we're going to pick c to be equal to 1. All right, so we're just going to pick this to be equal to 1. All right. Okay, and so now u prime is equal to, so I have u prime times this whole thing is equal to 1. So I can just divide by this. 1 over y1 squared times e to the integral of p dx, which is really, actually, yeah, I'll write this like this. So u is equal to the integral of all of that, and that whole stuff is really just all right, how do I say it? All right, so 1 over e to the integral of this thing is really the same as like e to the negative integral of p of x dx, and then I'll just keep that y1 squared in the bottom. And then u is just going to be the integral of that. If u1 prime is equal to that, then u1 is just equal to the integral of that. And since u is equal to, right, what was u equal to again? Yeah, u is, is equal to y2 over y1. We get the following. So here we have y2 over y1 is equal to this thing. So multiplying through by y1, we get y2 is equal to y1 times this whole crazy integral over here, this like integral of integrals thing. All right, and so this is the reduction of order formula. So you get a, so basically you normalize your differential equation. So take this thing, you normalize it right away. Then all you really need to know is like your p of x. Like the q of x doesn't really show up in the formula at all, but you need to know your p of x and you need to know what your y1 is, the solution that you already have. And then this formula right here will tell you what your second linearly independent solution is based off of that. So y1 and y2 do end up being linearly independent as claimed. You can check this by computing the Wronskian. It's equal to, remember, the determinant of y1 and y2, y1 prime, y2 prime, which would be y1 times y2 prime minus y2 times y1 prime. So what is y2 prime? Well, it's just like the derivative of this whole thing. And then y2 times y1 prime, oops. Y2, what was y2? Oh yeah, y2 is literally just that. And then times y1 prime. Okay, so I'm not going to work through all of this because computing the derivative of this, just, you can do it. It just ends up getting like pretty messy. I'm like happy enough just kind of doing this to just remind you what the determinant of a 2x2 matrix is, and then kind of push you towards like the next or the last step. When you do this, you basically end up getting, I think you end up getting e to the negative integral of p of x dx, which is not equal to 0 since e to the x is not equal to 0 for any x. It might not like exactly be e to the negative p of x. It might be like, I don't know, e to the positive p of x, or it's like something like that. I'm pretty sure that you just get like e to the something, and then you just conclude that's just not equal to 0. But not too important for now. The important thing is you can compute the Wronskian of this thing just in general and show that like no matter what, like your y1 and your y2, like these are both just going to be linearly independent, and this is going to be a solution to the differential equation. So you get a fundamental set, y1 and y2, where y2 is just equal to y1 times the integral of e to the negative integral of p of x dx divided by y1 of x squared, and then all of that integrated with respect to x. Okay. Great. So let's work some examples. So I'll show you how to do this first one, and then I recommend pausing the video and then trying the second one on your own, just kind of modeling what I do with the first one. All right, so we're just like straight up told that y equals x is a solution to this differential equation. And we're going to just assume that x is going to be positive. And then find the general solution based off of that. All right, so first thing that we need to always do is normalize our differential equation. So let's normalize by dividing by x squared. So we get y double prime minus x over x squared is just 1 over x. So then we get x plus 2 over x, y prime, plus x plus 2 over x squared times y. And that's equal to 0 over x squared, which is just 0. So what's our p of x? Our p of x is negative x plus 2 divided by x. Always remember to pay attention to whatever the sign of that is, right? So that negative is included in our p of x. So this is our formula for what y2 is going to be. So y1 is just equal to x. So then y2 is equal to y1 times the integral of e to the negative p of x dx all over y1 squared dx. And if I shove all that information into this formula, y1 is equal to x, e to the negative p of x. Let's move this down a little bit. E to the negative integral of p of x. P of x is negative x plus 2 over x dx, and over y1 squared, which is just x, so x squared. And then whatever that whole thing is, we just integrate that with respect to x. We get this nice double negative cancellation here. So we'll make those both positive. And then we just get e to the integral of x plus 2 over x, which we can split up into two fractions, x over x plus 2 over x. So this is x times the integral. By the way, remember, like, you can't, like, don't, like, pull out, like, an x squared or anything like that. Like, that you have to, like, be able to integrate this. Like, so deal with this entire integral. You can't bring this variable x in here, and you can't pull out an x squared. None of that stuff works. It's all garbage. Don't do any of that. It's just, like, stupid mistakes that I see. Don't do it. Integrate first. Okay. So we get e to the integral of x plus 2 over x, which we can write as x over x, which is 1, plus 2 over x dx. This is all over x squared. So we get x times the integral of e to the, and now what is this integral? Integral of 1 is just x. What's the integral of 2 over x? That is 2 ln of absolute value of x. We probably could just, like, drop the absolute values right away just because x is assumed to be positive, but whatever. Oh, by the way, when you're doing this, we're just searching for, like, a single solution for y2, so we don't have to, like, put a plus c here or anything like that. We're just looking for, like, one single function y2. When we give the general solution is going to be like c1 y1 plus c2 y2, so those c1 and c2s will more than make up for not putting a plus c over here. copying more stuff down just from previous steps. And then this is x times the integral of e to the x times e to the 2 ln of x, which is really ln of x squared. And of course, e to the ln of x squared is just x squared. So we get e to the x times x squared over x squared. Those cancel out. And then we're just left with the integral of e to the x dx, which is just e to the x. So we get x times e to the x for our final solution for y2. So this is our y2. Let's reread the problem, see if we answered everything. So given that this is a solution, find its general solution. So we didn't give its general solution, right? So we just found y2. We just found a second solution. So the general solution is going to be y equals c1 times our first solution, which is x, plus c2 times our second solution, y2, which is x e to the x. So that would be our general solution, and this would be our final answer here. Okay, so that's the general process for how you go about solving these types of problems. You normalize it, and then you figure out what's your p of x, and then you just kind of throw it into the formula. Maybe you're asked some extra stuff like what's the general solution, or in here, what's like the interval of solution, yada yada, and then just kind of go from there. So I recommend pausing the video and attempting example 2 on your own, and then unpausing and seeing if what you got matches with what I got. All right. I'm going to assume that you've paused and tried it now, and I'm just going to proceed. So your first step should just be to normalize. So we get y double prime plus 2x over 1 minus x squared. Y prime is equal to 0. So our formula is going to be y2 equals y1 times the integral of e to the integral of p of x dx over y1 squared dx. And our y1 is, okay, so it's telling us that y1 is just equal to 1. That's the solution. By the way, this is like actually really easy to check that this is y equals 1 is a solution to this, right? Because what is y1 prime? Y1 prime is just 0. What's y1 double prime? Y double prime is also equal to 0. So you get something times 0 plus something else times 0, which obviously equals 0, right? So pretty easy to check that that's a solution. And maybe you could argue even easy to just look at this and be able to just tell that this is a solution, right? And then so from there, just seeing that solution, you could just apply this formula to figure out what your other solution is. So we get e to the integral of, this is, I forgot a negative over here. This would be negative p of x dx, right? Yeah, so e to the negative p of x dx. That should be negative. So I get negative 2x over 1 minus x squared dx all over y1 squared. Y1 is just 1, so 1 squared. And then integrate that with respect to x. So, and then what's that equal to? So I'm going to stop putting all those 1s all over the place, and I get e to the integral. So I'm going to bring this negative inside. I'm going to multiply it by the denominators to make that denominator x squared minus 1 dx. And what does this become? So here you could do like a u sub. You could do like u is equal to x squared minus 1. Du is equal to 2x dx. And so this would just become e to the integral of 1 over u du. And then integrate that, whatever that result is, integrate that with respect to x. So I get e to the ln of u, which is x squared minus 1. So I'm going to sub that back in terms for x because I need to integrate again with respect to x anyways. Put that dx there. So we're done with that first integral. And now we have e to the ln of stuff, which is just stuff. So we get integral of x squared minus 1. And really it's absolute value of x squared minus 1. But we can just go ahead and drop those absolute values, assuming that we're working on an appropriate interval. So we have like 3 choices for what interval we want to work on. So like this differential equation, like we can't plug in 1 or -1, right? And the sign of like x squared minus 1, it's going to be positive if x is like bigger than 1 or less than -1. If you were to plug like -2 in here, you get -2 squared is positive 4, and then 4 minus 1 is going to be positive. But if you were to plug in anything between 1 and -1, so like a half or 0 or something like that, this thing will be negative. And so absolute value of x squared minus 1, you'd have to flip the sign. It's really 1 minus x squared. So let's just assume that we are on the interval 1 to infinity. You could also work on like -infinity to -1, or you could work on -1 to 1, but you would have to kind of flip the sign to make this like 1 minus x squared, just because, you know, that would be the positive thing there. So if we're on 1 to infinity, this is going to be fine, and then our solution would be 1/3 x cubed minus x. And again, we don't need the plus c here because we're just searching for a single solution. Yeah. So what's our general solution? It's going to be c1 times y1, and our y1 is just 1. So c1 times 1, you don't really even have to do the times 1. And then plus c2 times 1/3 x cubed minus x. And then our interval of solution is simply going to be 1 to infinity. All right, so that's it for the video. Hope that helped, and I'll see you in the next one.